The morning of September 1st, 1943, dawned hazy over Marcus Island, a tiny atoll roughly 1,000 nautical miles northwest of Wake Island. Lieutenant Takeo Tanimizu pulled his Mitsubishi, a 6M0, into a climbing turn, scanning the empty sky above him. His engine hummed with familiar confidence, the 940 horsepower Nakajima Sakai 12 radial that had carried him through 2 years of combat from China to the Solomons. Then he saw them, American fighters, diving from 25,000 feet with a speed that seemed impossible. These weren't the stubby wildcats he'd learned to outmaneuver. These were something new. Larger, heavier, menacing. The first one flashed past him in a near-vertical dive, its .650 caliber machine guns tearing through a nearby bomber formation before rocketing back skyward. Tanimizu pushed his throttle forward and hauled his Zero into pursuit. The lightweight fighter responded instantly, pulling through the turn with the knife-edge precision that had made Japanese naval aviation legendary. But when he tried to catch the American in the climb, something went wrong. The enemy fighter simply pulled away, not struggling, not clawing for altitude, but accelerating upward as if Tanimizu's Zero was standing still. For the first time in nearly 3 years of combat, a Japanese pilot realized that the performance advantage they'd counted on, the sheer speed that let them dictate every engagement, was gone. The Pacific War's first 18 months had taught American pilots a brutal lesson. The Mitsubishi A6M0 was faster than anything the United States Navy could put in the air. Not by enormous margins, perhaps, but by enough. Enough to chase down fleeing bombers. Enough to escape unfavorable fights. Enough to position for the perfect attack angle while American pilots struggled to respond. The numbers told the story with unforgiving clarity. The A6M2 Model 21, the variant that tore through Allied defenses from Pearl Harbor through Midway, achieved a maximum speed of approximately 332 miles per hour at 16,000 feet. Some Japanese pilots, using combat boost settings that pushed their engines beyond standard ratings, claimed to reach 345 miles per hour. The Grumman F4F Wildcat, America's primary carrier fighter through 1942, topped out at 318 miles per hour. That 14-mile-per-hour deficit, roughly 4% slower, was enough to make survival a matter of tactics rather than performance. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. American pilots developed the thatch weave, scissoring back and forth to provide mutual fire support. They learned never to dogfight with a Zero, never to try turning with an aircraft that could complete a full circle in 16 seconds. They mastered the boom and zoom, diving from altitude for a single firing pass, then using their diving speed to extend away before the Zero could respond. But these were defensive measures, adaptations born from inferiority. Squadron commanders filed urgent reports throughout 1942. The tactical situation was straightforward and grim. American pilots flying inferior aircraft were dying faster than the training pipeline could replace them. The strategic mathematics were even worse. Japan's carrier air groups, though suffering losses at Coral Sea and Midway, still fielded pilots with hundreds of combat hours. These men understood energy management intuitively, could judge deflection angles while pulling high G-turns, and flew aircraft optimized for exactly the kind of combat the Pacific demanded. The Zero's speed advantage wasn't just about raw velocity. It was about control, about choosing when to engage and when to extend away, about forcing opponents into predictable responses that could be exploited. Japanese doctrine emphasized this advantage explicitly. Attack from above when possible. Use superior speed to position before the enemy can respond. If caught low on energy, disengage rapidly, extend to safe distance, then reposition for another attack. American pilots reading these captured tactical manuals recognized that Japanese commanders understood exactly what their fighters could do and had built their entire doctrine around these capabilities. The speed differential created a psychological advantage as profound as any technical one. American pilots climbing into Wildcat cockpits knew they were slower. They knew that if they made mistakes, the Zero's performance would punish them fatally. This knowledge forced caution, restricted tactical options, and surrendered initiative to the Japanese. Fighter combat is fundamentally about energy. An aircraft's energy state consists of two components: kinetic energy, which is speed, and potential energy, which is altitude. A pilot can trade one for the other, diving to gain speed or climbing to gain height. But the total energy available depends on the aircraft's power-to-weight ratio and aerodynamic efficiency. The Zero achieved its performance through ruthless weight reduction. The aircraft weighed just 5,213 pounds fully loaded. It sacrificed armor plating, self-sealing fuel tanks, and structural strength that American and European fighters considered essential. This made the Zero extraordinarily vulnerable to battle damage, a weakness American pilots exploited whenever possible. But it also gave the lightweight fighter performance that conventional designs couldn't match. The Nakajima Sakai engine's 940 horsepower might seem modest, but pushing an airframe that weighed less than 3 tons translated to impressive speed and astonishing maneuverability. At low speeds, below 200 miles per hour, the Zero could outturn virtually every fighter in the world. Its controls remained responsive, where American fighters became sluggish. Japanese pilots trained to exploit this envelope, forcing opponents into slow-speed turning fights where the Zero's advantages were overwhelming. But speed was different. Speed required power and efficient aerodynamics. The Zero's clean lines and careful design gave it excellent speed for its power output. The problem was that the power output itself had limitations. The Sakai engine produced maximum power at around 16,000 feet, where the supercharger's single-stage design delivered optimal manifold pressure. Above that altitude, performance degraded. Below it, the engine produced less than maximum horsepower. This meant the Zero's speed advantage existed within a specific altitude band. American pilots who could force combat above 20,000 feet or below 10,000 often found the Zero less threatening. But tactical decisions about altitude aren't made in isolation. They depend on mission requirements, enemy positioning, and the broader combat situation. Bomber escorts can't just climb higher if it means abandoning the aircraft they're protecting. Combat air patrols must intercept threats at whatever altitude those threats appear. The reality was that most Pacific air combat happened between 10,000 and 20,000 feet, right where the Zero performed best. Grumman Aircraft Engineering Corporation's engineers in Bethpage, New York, understood the problem with perfect clarity by mid-1942. Combat reports from the Pacific filled filing cabinets. Pilot debriefs provided specific, actionable intelligence about what worked and what didn't. The company had been working on a Wildcat successor since 1941, but Pearl Harbor and the subsequent disasters in the Philippines and Dutch East Indies added urgent pressure. The design team, led by Chief Engineer William Schwendler and overseen by company founder Leroy Grumman himself, faced a fundamental question. Could they build a carrier fighter that matched or exceeded the Zero's speed while retaining the ruggedness and firepower that kept American pilots alive? The answer required more than incremental improvements. It demanded a completely different approach to power and design philosophy. The first prototype, designated XF6F1, used a Wright R2600 Cyclone engine, producing 1,600 horsepower. Test flights in June 1942 showed promise, but not excellence. The aircraft was faster than the Wildcat, certainly, but not dramatically so. Engineers calculated that even with refinements, this configuration might achieve perhaps 340 to 350 miles per hour. That would barely match the Zero, not exceed it. The breakthrough came from persistence and bureaucratic audacity. Engineers at the Bureau of Aeronautics, specifically Commander George Anderson and Lieutenant Commander Abe Vossler, had been tracking development of Pratt and Whitney's R2800 double wasp engine. This was an 18-cylinder, 2-row radial powerhouse producing 2,000 horsepower, a 40% increase over the proposed Cyclone. The problem was allocation. Every R2800 engine was already assigned to either the Republic P-47 Thunderbolt or the Vought F-4U Corsair programs. Navy bureaucracy didn't permit swapping engines between programs without extensive approval processes. Anderson and Vossler bypassed the system entirely. They essentially commandeered an R2800 engine, had it delivered to Grumman's factory, and told the engineers to install it in the second F6F prototype. The test pilots were stunned by the results. The XF6F3, as the redesigned aircraft was designated, first flew on July 30th, 1942. Maximum speed jumped to 376 miles per hour at 23,000 feet. Some variants with water injection and optimized finishes later achieved 380 to 391 miles per hour. These weren't incremental improvements, they were transformative. The Hellcat was now faster than the Zero at all altitudes, not by trivial amounts either. At sea level, the Hellcat held roughly a 20-mile-per-hour advantage. At 15,000 feet, the gap widened to 30 or 35 miles per hour. At 25,000 feet, where the Zero's single-stage supercharger struggled in thin air, the Hellcat's two-stage supercharged engine still delivered strong performance while Japanese fighters gasped for power. Speed alone didn't guarantee victory, though history is littered with examples of faster aircraft that still lost dogfights to slower, more maneuverable opponents. The Hellcat's genius was that it paired speed with everything else that mattered. The R2800 engine's 2,000 horsepower turned a 13-foot Hamilton Standard constant-speed propeller. This massive propeller, working in concert with the powerful engine, gave the Hellcat acceleration that changed tactical calculations fundamentally. A Wildcat pilot caught low and slow by a diving, Zero had limited options. Try to run, and the Zero would catch him. Try to fight, and the Zero would outmaneuver him. A Hellcat pilot in the same situation could simply firewall the throttle and extend away. The Zero couldn't catch him. The heavier American fighter would pull ahead, opening distance until the pilot could safely climb back to altitude and reset for another engagement. This capability gave Hellcat pilots initiative. They could choose to fight or to disengage. They could accept combat when conditions favored them and refuse it when circumstances didn't. This was the same advantage Japanese pilots had enjoyed for 2 years, now reversed. The design philosophy behind the Hellcat's speed involved more than just engine power. Aerodynamic efficiency mattered tremendously. Grumman engineers obsessed over every source of drag. The engine cowling was designed for smooth airflow, with carefully positioned cooling louvers that minimized disruption to the slipstream. The fuselage was relatively clean despite the need to accommodate armor, ammunition, fuel tanks, and a large pilot. The wings, though big at 42 feet 10 inches of span, used an efficient airfoil section that generated lift without excessive drag. Landing gear retracted fully into the wings rather than the fuselage, creating a cleaner profile. The hydraulic retraction system meant pilots didn't have to hand-crank 35 turns like Wildcat pilots did, but more importantly, it allowed the gear to stow completely, eliminating drag. Even small details mattered. Grumman engineers flush-riveted critical areas of the fuselage and wings, eliminating the tiny protrusions that conventional rivets created. They faired the gun barrels and ammunition chutes carefully. They used smooth, polished paint finishes on production aircraft. Each of these refinements recovered a few miles per hour, and those small gains accumulated into meaningful performance advantages. The Hellcat's weight was substantial compared to the Zero. Fully loaded for combat, an F6F3 weighed approximately 12,400 pounds, more than twice the Zero's combat weight. This should have been devastating for performance. Heavy aircraft accelerate slowly, climb poorly, and struggle in turning fights. But the R2800's massive power overcame the weight penalty. The power-to-weight ratio, measured in horsepower per pound, determined how effectively an aircraft could convert engine power into acceleration and climb performance. The Zero achieved its maneuverability and climb rate with a power-to-weight ratio of approximately 0.18 horsepower per pound. The Hellcat, despite being so much heavier, achieved 0.16 horsepower per pound. The difference was small enough that in practical combat conditions, especially above 10,000 feet, the Hellcat could climb and accelerate nearly as well as the Zero, while also being substantially faster in level flight. This combination of speed and power fundamentally changed what carrier fighters could do. Previous American fighters had to avoid prolonged engagements, get in, take a shot, get out before the more maneuverable Japanese fighters could respond. The Hellcat could stay in the fight. It could absorb hits that would destroy a Zero, thanks to armor and self-sealing tanks. It could deliver devastating firepower from 650 caliber machine guns. And critically, it could control the engagement tempo through superior speed. When Hellcats began reaching Pacific carrier squadrons in early 1943, squadron commanders received detailed briefings on the aircraft's capabilities. The speed advantage was emphasized explicitly. Tactical doctrine evolved rapidly to exploit this advantage. Fast and high became the guiding principle. Hellcat formations would position themselves above expected Japanese approach routes. When enemy aircraft appeared, American pilots would dive from altitude, using gravity to add even more speed to their already fast fighters. They would make high-speed firing passes through enemy formations, then use that accumulated speed to zoom back up to altitude, where the Zeros couldn't effectively pursue. This tactic worked because of basic physics. In a dive, every aircraft accelerates due to gravity, but terminal velocity, the maximum speed achievable in a dive, depends on power, weight, and drag. The Hellcat's sturdy construction and powerful engine let it dive faster than the Zero without risking structural failure. Japanese pilots who tried to follow Hellcats down found themselves rapidly falling behind, and if they pushed too hard, their aircraft's less robust construction would begin to fail. American intelligence officers tracking Japanese radio communications and interrogating prisoners began noticing changes in Japanese tactical discussions during late 1943. The tone shifted from confidence to concern. Captured documents described the new American fighter as unexpectedly fast and warned pilots to avoid prolonged pursuits. By December 1943, formal tactical bulletins were being distributed to Japanese naval aviation units throughout the Pacific. These documents acknowledged that the new Grumman fighter possessed speed equal to or exceeding the Type 0 and recommended different engagement tactics. The recommendations were telling. Avoid horizontal speed contests with the new American fighter. Try to force vertical maneuvering where the Zero's lighter weight might provide advantages. Do not pursue American fighters that disengage by accelerating away. These were defensive instructions, the kind of tactical guidance issued when your equipment is outmatched. Japanese pilots reading these bulletins understood implicitly that the situation had changed fundamentally. The Marcus Island engagement on September 1, 1943, was one of the first large-scale combats where Hellcats and Zeros met. The Americans attacked with confidence, their pilots briefed on the Hellcats' capabilities and trained in tactics specifically designed to exploit them. Japanese pilots defending the island faced an unpleasant surprise. The American fighters were faster, climbed nearly as well, and could simply refuse to fight when conditions didn't favor them. Lieutenant Commander Edward Butch O'Hare, already famous as a Medal of Honor recipient and one of the Navy's most experienced fighter tacticians, had helped develop the Hellcat's employment doctrine. His insight was straightforward: use the speed advantage to control every aspect of combat, force Japanese fighters to respond to American initiatives, make them fight at altitudes, speeds, and geometries where the Hellcat's advantages were maximized and the Zero's strengths were minimized. O'Hare emphasized that the Hellcat couldn't outturn a Zero in slow-speed combat. That limitation remained. But the Hellcat's speed meant pilots never had to accept slow-speed turning fights. They could always accelerate away, reset, and attack again from positions of advantage. This was combat on American terms, not Japanese terms. Over Tarawa in November 1943, the pattern repeated. Hellcats from multiple carriers engaged defending Zero fighters. The Americans shot down 30 Japanese aircraft for the loss of one Hellcat. The kill ratio was remarkable, but what mattered more was how the combat unfolded. Japanese pilots found themselves unable to dictate engagement terms. They couldn't catch Hellcats that chose to disengage. They couldn't escape from Hellcats that chose to pursue. The fundamental dynamic of Pacific air combat had reversed. Japanese commanders recognized the problem but struggled to address it. The Zero had been designed in 1937 and 38, reflecting that era's understanding of fighter requirements. Modifications and improvements had been made, certainly. The A6M3, introduced in 1942, had a more powerful engine and improved performance. The A6M5, entering service in late 1943, pushed maximum speed to 351 miles per hour at 20,000 feet. But these were incremental improvements to a fundamentally compromised design. The Zero's lack of armor and self-sealing tanks remained. Its structural limitations prevented higher speed operations. Most critically, Japan's industrial capacity couldn't produce engines powerful enough to overcome these limitations while maintaining the aircraft's other advantages. The Japanese aircraft industry attempted to develop Zero replacements. The Mitsubishi J-2M Raiden and Kawanishi N-1K Shiden showed promise, both featuring more powerful engines and improved performance. But production problems plagued both programs. The Raiden's engine proved temperamental and prone to overheating. The Shiden's complex landing gear design, adapted from its floatplane ancestor, caused maintenance nightmares. Neither aircraft entered service in sufficient numbers to challenge American air superiority. By mid-1944, Japanese naval aviation faced a compounding crisis. The Hellcat's speed advantage was bad enough, but pilot quality degradation made everything worse. Pre-war Japanese training had been extraordinarily thorough, producing pilots with 300 to 700 flight hours before joining operational squadrons. Combat consumed these skilled aviators faster than the training system could replace them. New pilots arriving at squadrons by 1944 had 100 to 150 hours of training, sometimes as few as 40 hours. These barely trained pilots faced American aviators with 300 hours of training, plus extensive combat experience, flying aircraft with superior speed and firepower. The combination was catastrophic for Japan. Inexperienced pilots couldn't exploit the Zero's remaining advantages in low-speed maneuverability. They made predictable mistakes that experienced Hellcat pilots punished ruthlessly. The speed disparity meant these novice Japanese pilots couldn't even choose to disengage from unfavorable combat. Hellcat pilots could pursue them relentlessly, and the new Japanese pilots lacked the skill to evade. Strategic circumstances compounded the tactical problems. By late 1943, Japan was fighting defensively. Japanese fighters had to protect fixed locations, shipping routes, and critical installations. They couldn't choose when to fight, because they had to defend these assets whenever American forces attacked. The initiative belonged entirely to the Americans, who could concentrate overwhelming force at times and places of their choosing. The Hellcat's speed advantage meant American carrier task forces could launch strikes, achieve air superiority over the target, and return to their carriers before Japanese reinforcements could arrive. Even when Japanese fighters did arrive, they couldn't catch the withdrawing Hellcats. The American fighters simply ran away at speeds the Zeros couldn't match. Fuel availability made everything worse. Advanced pilot training requires extensive flight hours. Japan's dwindling petroleum supplies meant training programs were cut shorter still. Operational squadrons received reduced fuel allocations, limiting their ability to maintain proficiency through practice flying. Some units couldn't afford any training flights at all. Pilots only flew during actual combat missions, meaning they never developed the skills needed to exploit their aircraft's capabilities or counter enemy advantages. You cannot maintain edge-of-envelope performance, the kind of high-speed combat maneuvering required to survive against Hellcats, without regular practice. Japanese pilots were arriving at combat squadrons without the arst, muscle memory, and instinctive responses that separate survivors from casualties. Facing faster American fighters with better-trained pilots was simply execution. The Battle of the Philippine Sea in June 1944 demonstrated the Hellcat's dominance with brutal mathematical precision. Admiral Mark Mitcher's Task Force 58 deployed 15 carriers with 956 aircraft, including 475 Hellcats. Vice Admiral Jisaburo Ozawa's mobile fleet launched waves of aircraft from 9 carriers, determined to destroy the American invasion force off Saipan. The engagement that followed would be forever called the Great Marianas Turkey Shoot. American radar detected the first incoming Japanese raid at 10 a.m. on June 19th, at a distance of 150 miles. This early warning gave Hellcat pilots time to climb to optimal interception altitude. Commander David McCampbell, leading the Essex Air Group, positioned his Hellcats at 25,000 feet, more than 4 miles above the ocean. When Japanese formations appeared below at 18,000 to 20,000 feet, American pilots held overwhelming advantages. They had altitude, they had radar vectors providing perfect positioning, and they had aircraft that could dictate every term of engagement. McCampbell's famous radio transmission captured the moment. All guns, this is base. Vector 270. Climb to Angels 25. Hellcat streamed toward the incoming threat with disciplined precision. The first wave of 69 Japanese aircraft hit American defenses like a tsunami against a seawall. Hellcats dove from altitude, ripped through the formations with devastating gunnery, then climbed back to altitude while Japanese pilots tried desperately to respond. Zeros that attempted to climb after their attackers found themselves in exactly the situation American doctrine intended. Low on energy, vulnerable, unable to catch their tormentors. Those who dove away to maintain speed simply took themselves out of the fight, unable to threaten American ships while Hellcats controlled the altitudes above. The speed disparity was crushing. A Hellcat diving from 25,000 feet could easily reach 400 miles per hour or more. Making a firing pass at that speed, then converting that velocity into a climb back to altitude, was straightforward for well-trained American pilots. Japanese pilots had no effective counter. They couldn't climb fast enough to intercept before the Americans repositioned. They couldn't run fast enough to escape pursuit. They were fighting a battle where every advantage belonged to the enemy. Lieutenant Alex Vrasiu, flying from USS Lexington, intercepted a formation of 50 Japanese dive bombers with minimal fighter escort. In a single engagement lasting 8 minutes, he shot down 6 aircraft. His tactical report described the pattern clearly. Use altitude advantage to make repeated diving. Attacks. Climb away after each pass. Never allow yourself to be drawn into turning combat. Never give the enemy the fight they're trained for. The second Japanese wave of 100 to 30 aircraft fared no better. American fighter directors watching radar plots vectored fresh Hellcat squadrons into perfect interception positions. The Japanese formation fragmented under constant attacks from above. Pilots who tried to maintain formation discipline became predictable targets. Those who broke formation to engage individually lost mutual support and fell to coordinated American tactics. Wave 3 consisted of 47 aircraft. Wave 4 numbered 82. Both met systematic destruction. By the end of June 19th, Japanese naval aviation had lost approximately 243 carrier aircraft and 50 land-based aircraft. American losses totaled 29 aircraft, most falling to anti-aircraft fire rather than aerial combat. The kill ratio exceeded 10 to 1. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Several Hellcat pilots achieved ace status in a single day. Ensign Wilbur Spiderweb shot down 6 aircraft. Lieutenant Junior Grade William Bill Stewart claimed 5. The tactical pattern was identical across dozens of individual engagements. Hellcats used speed to control combat geometry. Japanese pilots couldn't force the Americans to fight on Japanese terms. The speed advantage that Japanese pilots had enjoyed from 1941 through early 1943 was now comprehensively reversed, and Japanese tactics had no answer. June 20th brought a desperate Japanese retreat and an aggressive American pursuit. As Japanese carriers fled westward, American strikes launched at maximum range. knowing pilots would face nighttime carrier recoveries after exhausting their fuel. Hellcats escorted the strike packages, and when Japanese combat air patrol rose to intercept, American fighters used their familiar tactics. Dive, attack, extend. Japanese pilots, already demoralized and exhausted, broke off combat rather than accept engagements they knew they couldn't win. The two-day battle cost Japan over 600 aircraft and 3 carriers sunk. American carrier aviation had achieved absolute air superiority, and the Hellcat's speed was the foundation that made everything else possible. Japanese after-action reports from the Philippine Sea revealed the depth of the crisis. Pilots reported that American fighters could choose when to engage and when to break off entirely through superior speed. Multiple reports mentioned the frustration of watching Hellcats simply fly away when Japanese fighters attempted to close for combat. One particularly bitter assessment noted that American tactics had reduced Japanese fighters to helpless targets. They attack from above with great speed. When we attempt a pursuit, they climb away faster than we can follow. When we attempt to disengage, they pursue faster than we can flee. There is no altitude and no situation where our aircraft holds advantage. This wasn't a tactical adaptation. This was an acknowledgement of comprehensive technical inferiority. The Zero's maneuverability advantage remained, certainly. In slow-speed turning fights, the Japanese fighter could still outturn the Hellcat. But Hellcat pilots never accepted slow-speed turning fights. The speed advantage meant they never had to. Japanese commanders understood they needed new aircraft, but understanding didn't equal capability. The Mitsubishi A-7M Reppu was designed as the Zero's successor, featuring a 2,000 horsepower engine and performance designed to match or exceed American fighters. But development problems delayed the program repeatedly. Engine reliability issues, structural challenges, and material shortages meant the Reppu never reached operational service before the war ended. The Kawanishi N-1K2J Shiden Kai, an improved version of the earlier Shiden, entered production in late 1944. This was an excellent aircraft, with a 2,000 horsepower engine and performance competitive with the Hellcat. But production never exceeded about 400 examples. Too few, too late. Even when these superior Japanese fighters reached frontline squadrons, pilot quality had degraded so severely that the aircraft's capabilities couldn't be fully exploited. A talented veteran pilot in a Zero was more effective than a novice pilot in a theoretically superior Shiden. The training pipeline collapse was killing Japanese naval aviation more surely than any combat loss. By late 1944, new Japanese pilots arrived at squadrons with 100 to 150 flight hours total. Some had as few as 40 hours. These barely trained aviators faced American pilots who averaged 300 flight hours plus extensive gunnery and tactical training. The skill disparity combined with the equipment disparity created a compounding catastrophe. Individual Japanese pilots did adapt where possible. Warrant Officer Saburo Sakai, one of Japan's top surviving aces, described in his memoir how he modified his tactics after encountering Hellcats. He avoided any situation where speed mattered. He used hit-and-run attacks from favorable positions only, engaging only when he had overwhelming positional advantage. Then he disengaged immediately before American fighters could respond. But Sakai was exceptional, a survivor with over 500 combat missions. His tactics required judgment and skill that new pilots couldn't replicate. One veteran could adapt. Squadrons full of novices couldn't. The psychological impact of the speed reversal was profound. For 2 years, Japanese pilots had approached combat with confidence, built on technical superiority. They knew their aircraft was faster, more maneuverable, longer ranged than anything they faced. Now their commanders were telling them to avoid specific types of engagement with specific American aircraft. That's not a tactical adaptation. That's acknowledgement of inferiority. American signals intelligence monitoring Japanese radio frequencies captured the shift in tone. Radio communications during engagements changed from aggressive to defensive. Japanese pilots warning each other not to pursue Hellcats that were climbing away. transmissions advising flights to break off and return to base rather than accept combat. The hunter mentality had been replaced by hunted desperation. One intercepted transmission from late 1944, translated by Fleet Radio Unit Pacific, read simply, "They are too fast. Do not engage unless positioned with overwhelming advantage." The brevity spoke volumes about Japanese awareness of their situation. By 1945, the strategic collapse was complete. American carrier task forces operated with near impunity off the Japanese home islands. Hellcat combat air patrols established what pilots called the Big Blue Blanket, continuous air coverage that Japanese aircraft couldn't penetrate effectively. When Japanese aircraft did attempt to attack American carriers, they faced overwhelming numbers of Hellcats positioned at altitude with speed advantage and pilot skill advantage. The mathematics were impossible. The Hellcat's final combat record reflected its dominance: 5,223 enemy aircraft destroyed in aerial combat, 306 additional aircraft destroyed on the ground, all achieved at a loss of only 270 Hellcats in air-to-air combat. That 19-to-1 kill ratio represented the most lopsided aerial victory margin of any major fighter aircraft in World War II. No other fighter, not the Spitfire, not the Mustang, not the Messerschmitt, Me-109, achieved anything comparable. Every other advantage, the heavy armament, the rugged construction, the pilot armor, mattered tremendously. But the ability to control engagement tempo through superior speed made everything else possible. American pilots could choose when to engage and when to extend away. They could position themselves for optimal attacks and withdraw before Japanese fighters could respond effectively. They could escape unfavorable situations by simply accelerating to speeds where pursuing aircraft couldn't follow effectively. This flexibility was unprecedented in Pacific carrier operations. Individual pilot achievements illustrated the Hellcat's effectiveness when flown by skilled aviators who understood how to exploit its speed advantage. Captain David McCampbell's 34 confirmed kills made him the Navy's top ace. Commander Cecil Harris finished with 24 victories, all in Hellcats. Lieutenant Eugene Valencia developed the mowing machine tactical formation that paired fighters in mutually supporting elements optimized for speed-based tactics. He finished with 23 kills. These weren't just talented pilots. They were tacticians who understood that speed control meant combat control. Valencia's mowing machine formation exemplified the evolution of American tactics around the Hellcat's capabilities. 4 aircraft operating in 2 pairs, with one pair positioned high and fast, ready to dive on any threat. The second pair slightly lower, engaging targets directly while the high pair provided overhead cover. If Japanese fighters attempted to pursue the engaging pair, the high pair would dive through them at devastating speed. If the engaging pair needed to disengage, their speed let them extend away while the high pair covered their withdrawal. This formation was only possible because Hellcats could maintain the speed necessary to make rapid position changes. Slower fighters couldn't execute these tactics. The speed margin wasn't enormous in absolute terms, 50 miles per hour difference between a Hellcat at maximum speed and a 0 at maximum speed. But in combat, that margin meant the difference between controlling engagements and being controlled. It meant being able to choose your fights instead of accepting whatever the enemy offered. Japanese pilots who survived the war acknowledged the Hellcat's impact in post-war interviews. Saburo Sakai stated that the Hellcat's introduction marked the turning point in Pacific air combat. Other veterans described the psychological impact of facing an opponent that controlled engagement terms completely. The warrior culture that had sustained Japanese military effectiveness couldn't overcome fundamental material disadvantage. The F6F Hellcat's legacy isn't just in the statistics, though the numbers are staggering. It's in the fundamental shift it created in Pacific air warfare. Before the Hellcat, American pilots fought defensively, using tactics to compensate for inferior equipment. After the Hellcat, American pilots fought offensively, using superior speed to dictate every aspect of combat. The doctrinal revolution shaped jet-age air combat, and continues influencing fighter tactics into the 21st century. Modern fighter doctrine still emphasizes energy management and speed control. The concepts that Hellcat pilots refined through thousands of combat missions, using speed to control combat geometry and force opponents into disadvantageous situations, remain foundational to how air superiority fighters are designed and employed. Production numbers reflected the Hellcat's strategic importance and American industrial capacity. Grumman's Bethpage facility produced 12,275 F6F Hellcats between 1942 and November 1945, when production ended weeks after Japan's surrender. At peak production, in March 1945, the factory delivered 605 aircraft in a single month, an average of more than 20 Hellcats per day. This industrial achievement meant American carriers never lacked aircraft regardless of combat losses. Every damaged Hellcat could be replaced within weeks, sometimes days. Japanese factories, struggling under Allied bombing and raw material shortages, couldn't replace losses at anywhere near this rate. The material advantage compounded the tactical advantage. The Hellcat remained in frontline service until the end of the war, then was rapidly phased out as jet aircraft entered service. By 1954, the last Hellcats had been retired from active duty, but during its operational period from 1943 to 1945, no aircraft contributed more to American victory in the Pacific. The speed that Japanese pilots had counted on for 2 years, the performance margin that let them dictate combat on their terms, was gone. And with it went Japanese naval aviation's ability to challenge American air superiority. Dangerous aircraft in skilled hands throughout the war. Its maneuverability at low speeds was never matched by American fighters. But skilled hands became increasingly rare as the war progressed, and maneuverability alone couldn't compensate for speed, disadvantage, and numerical inferiority. The final battles of 1945 saw Japanese pilots, often flying their first or second combat missions, facing American veterans in aircraft with every conceivable advantage. The outcome was never in doubt. The Hellcat's retirement from frontline service came swiftly after Japan's surrender. By 1946, newer aircraft were already replacing the workhorse fighter on American carrier decks. The Grumman F6F Bearcat, smaller and more maneuverable than the Hellcat while retaining similar power, became the Navy's new standard fighter. The Bearcat could reach 450 miles per hour and climb at over 4,000 feet per minute, performance that made even the Hellcat seem outdated. But the Bearcat arrived too late to see combat in World War II, and the jet age was already dawning. The first jet-powered carrier aircraft, the McDonnell FH-1 Phantom, flew in January 1945. By 1950, jets were rapidly displacing piston-engine fighters across all services. The Hellcat's combat career had lasted barely 2 years, from September 1943 through August 1945, yet in that brief window it had fundamentally altered the course of the Pacific War. Most Hellcats were scrapped or placed in storage by 1948. The massive wartime production that had churned out over 12,000 aircraft created a surplus that peacetime budgets couldn't justify maintaining. Storage facilities across the United States filled with mothballed Hellcats, their guns removed, their engines preserved with protective coatings against corrosion. Many would never fly again. Some were sold as scrap metal, their aluminum recycled, into peacetime products. Others became gate guards at naval air stations, static displays commemorating the victory they'd helped achieve. But select Hellcats found new roles that extended their service lives in unexpected ways. The F6F Newton's night fighter variants, equipped with radar and specialized instrumentation, remained in Naval Reserve squadrons until 1954. These aircraft filled training roles, teaching new generations of naval aviators the fundamentals of carrier operations and night intercepts. The radar technology they carried, cutting edge in 1944, became training equipment for operators learning the principles that would apply to far more sophisticated systems in jet aircraft. The most unusual Hellcat missions came during the Korean War, when obsolete F6F fighters were converted into remotely controlled drones. Designated F6F5K, These unmanned aircraft were loaded with 2,000-pound bombs and directed toward heavily defended targets that would have been suicidal for manned aircraft. In late 1952, Guided Missile Unit 90 operated from USS Boxer, launching F6F F5K drones against North Korean bridges and power plants. An accompanying Douglas AD Skyraider served as the control aircraft, with a pilot watching a television camera mounted in the drone's cockpit and guiding it via radio signals. The concept was primitive by modern standards, essentially creating cruise missiles from obsolete fighters. The results were mixed. Of 6 drone missions flown, only 1 successfully hit its designated target. 4 missed completely, and 1 aborted due to technical malfunctions. The television guidance system proved unreliable, signal interference was common, and the drones lacked the sophisticated targeting systems that would characterize later precision weapons. One particularly memorable incident saw a rogue F6F F5K, its control signals lost, flying independently across North Korean airspace, while jet fighters scrambled unsuccessfully to shoot it down before it crashed harmlessly into a hillside. Despite limited tactical success, these missions represented important steps toward modern unmanned combat aerial vehicles. The F6F F5K demonstrated that remotely controlled aircraft could reach and attack targets, even if accuracy remained problematic. Future drone development would refine these concepts, eventually producing the sophisticated unmanned systems that dominate 21st-century warfare. Foreign operators kept Hellcats flying longer than American forces did. The British Royal Navy's Fleet Air Arm received 1,263 Hellcats under Lend-Lease agreements during the war. Initially designated Gannet Mark I, they quickly adopted the American name. British Hellcats operated in the Atlantic, Mediterranean, and Pacific theatres, providing combat air patrol for carrier task forces and supporting amphibious operations. British pilots appreciated the aircraft's ruggedness and reliability, characteristics that proved valuable in the harsh operating conditions of North Atlantic convoy duty. After the war, Britain returned most Hellcats to American custody, but some remained in service through 1946 for training purposes. The French Navy purchased over 100 surplus American Hellcats between 1950 and 1953, operating them from carriers during the Indochina War. French F6F 5 seconds flew ground attack missions supporting French colonial forces fighting Viet Minh insurgents. These aircraft were painted in glossy sea blue with modified French roundels featuring anchor symbols. French pilots found the Hellcat's bomb-carrying capacity and sturdy construction ideal for close air support missions over jungle terrain. The aircraft could absorb ground fire that would down more fragile fighters, and its 650 caliber machine guns provided devastating firepower against ground targets. French Hellcat operations continued until 1954, when the Indochina War ended with French defeat at Dien Bien Phu. Uruguay's navy operated Hellcats longer than any other force, keeping them in active service until 1961. The Uruguayan Naval Aviation Arm used Hellcats primarily for maritime patrol, training, and occasional ceremonial duties. This extended service life testified to the aircraft's fundamental soundness and ease of maintenance. Even with limited spare parts availability and aging airframes, Uruguayan maintainers kept their Hellcats flying for 16 years after the war ended. The last operational Hellcat flight anywhere in the world occurred in Uruguay, marking the final chapter of the type's military service. The Hellcat's influence on post-war American fighter development extended far beyond its direct successors. The tactical doctrines developed around the Hellcat's capabilities, particularly energy management and boom and zoom tactics, became foundational concepts for jet fighter employment. When the Navy transitioned to jets like the F9F Panther and F2H Banshee during the Korean War, pilots applied lessons learned in Hellcats to these new aircraft. Speed still mattered. Altitude still provided a tactical advantage. Energy conservation still determined who controlled engagements. These principles transcended technology changes. The Top Gun Naval Fighter Weapons School, established at Naval Air Station Miramar in 1969, still teaches concepts that Hellcat pilots refined during World War II. Modern fighter pilots learn about energy states, how to use speed and altitude to dominate opponents, and how to force enemies into disadvantageous situations. These are the same principles that David McCampbell and his contemporaries employed against Japanese Zeros. The aircraft have changed dramatically, from piston engines to jets to supersonic fighters, but the fundamental physics of air combat remain constant. A pilot who understands energy management will defeat one who doesn't, regardless of what aircraft they're flying. Fighter design philosophy also bears the Hellcat's imprint. American aircraft designers learned from the Hellcat that ruggedness and reliability matter as much as pure performance. The best fighter isn't necessarily the fastest or most maneuverable, but the one that combines good performance with durability, maintainability, and ease of operation. This philosophy influenced designs throughout the jet age. The F-15 Eagle, introduced in 1976, emphasized robust construction and multiple redundant systems to ensure mission completion even with battle damage. The F/A-18 Hornet, which became the Navy's primary carrier fighter in the 1980s, prioritized reliability and ease of maintenance over absolute maximum performance. The Hellcat's success also validated the importance of pilot protection. Self-sealing fuel tanks, armor plating, and robust construction saved countless American lives during World War II. These features became standard in all subsequent American fighters. Soviet aircraft designers, who had traditionally prioritized performance over pilot protection, began incorporating similar features after studying captured American aircraft. The global trend toward better pilot protection can be traced directly to lessons learned from aircraft like the Hellcat. Modern pilots who fly F/A-18 Super Hornets or F-35C Lightning IIs benefit from design philosophies established 80 years ago. Museum collections worldwide preserve Hellcats as monuments to their wartime achievements. The Smithsonian's National Air and Space Museum displays an F6F, its paint scheme representing the aircraft flown by Medal of Honor recipient Lieutenant Commander Butch O'Hare. The National Naval Aviation Museum in Pensacola, Florida, maintains several Hellcats in its collection, including an F6F Newton's night fighter variant with its radar installation intact. The American Heritage Museum houses an F6F Newtons restored to flying condition, one of only a handful of airworthy Hellcats remaining worldwide. Warbird enthusiasts prize the few flyable Hellcats for airshow demonstrations. These restored aircraft, maintained by dedicated teams of mechanics and historians, provide living connections to the Pacific War. When a Hellcat's R-2800 engine roars to life, when the massive propeller begins turning, audiences can experience something approximating what carrier deck crews heard every day during 1943 through 45. The visceral power of that 18-cylinder radial engine, the sight of the stubby fighter rolling down the runway, these sensory experiences connect modern viewers to history in ways that photographs and films cannot. Pilots who have flown restored Hellcats consistently describe the aircraft as honest and forgiving. It doesn't have vicious stall characteristics or tricky handling quirks. The controls are heavy compared to lighter fighters, but responsive and predictable. Visibility from the cockpit is excellent, thanks to the bubble canopy and the pilot's elevated seating position. The aircraft feels solid, substantial, like a machine built to absorb punishment and keep flying. These qualities made it ideal for young, relatively inexperienced pilots during the war, and they make it a pleasure to fly for modern aviators accustomed to far more sophisticated aircraft. The statistical record of the Hellcat remains unprecedented. 5,223 enemy aircraft destroyed in aerial combat. A 19-to-1 kill ratio that no other major fighter of World War II approached. 75% of all U.S. Navy aerial victories in the Pacific were attributed to Hellcat pilots. These numbers represent not just technical superiority but the culmination of effective design, sound tactics, and industrial capacity working in perfect synchronization. The speed advantage that allowed Hellcat pilots to dictate combat terms was the foundation upon which everything else rested. Without that fundamental performance superiority, tactics would have been less effective, pilot skills would have mattered less, and the kill ratio would have been far more balanced. The Japanese Zero pilots who encountered Hellcats in combat carried that experience with them after the war. Survivors like Saburo Sakai, who wrote extensively about his combat experiences, consistently emphasized how the Hellcat changed everything. In his memoir Samurai, Sakai described the psychological impact of facing an opponent that controlled every aspect of combat. We could not catch them when they chose to leave. We could not escape when they chose to pursue. The Americans had learned from their defeats in 1942, and they built an aircraft that turned our advantages into weaknesses. Other Japanese veterans expressed similar sentiments in post-war interviews. The realization that their speed advantage was gone, that American fighters now held superior performance, marked a psychological turning point as significant as any tactical defeat. Warriors who had dominated Pacific skies suddenly found themselves outmatched, and no amount of fighting spirit could overcome the material disparity. This acknowledgement of American technical superiority continued affecting Japanese military thinking throughout the Cold War and into the modern era. When the Japanese government reconstituted its military forces as the Japan Self-Defense Forces in the 1950s, they prioritized acquiring the most advanced equipment available rather than attempting to rely on superior training or fighting spirit alone. The lessons learned fighting Hellcats had permanent impact on Japanese military doctrine. The legacy of the F6F Hellcat extends beyond military history into broader narratives about American industrial capability and wartime mobilization. The fact that Grumman could design, test, and put into mass production an aircraft as effective as the Hellcat in under 18 months demonstrated American engineering and manufacturing prowess. The peak production rate of over 600 aircraft per month in March 1945 represented industrial capacity that Japan could never hope to match. This production superiority, combined with the Hellcat's technical advantages, created an insurmountable advantage. For every Hellcat shot down, 2 or 3 more rolled off production lines to replace it. Japanese factories, struggling under Allied bombing and raw material shortages, couldn't replace their losses at anywhere near comparable rates. The war became an attritional struggle that Japan couldn't win, and the Hellcat was the weapon that ground Japanese naval aviation into dust. The human stories behind the statistics remain the most compelling aspect of the Hellcat's legacy. Every one of those 5,000-plus victory credits represents a combat engagement where an American pilot faced mortal danger and emerged victorious. Many of those pilots were barely 20 years old, young men who'd been civilians months earlier, now fighting for their lives over vast oceanic distances thousands of miles from home. The Hellcat gave them a fighting chance. It gave them an aircraft that wouldn't burst into flames from a single hit. It gave them firepower that could destroy enemy aircraft decisively. And critically, it gave them speed that let them choose whether to fight or flee. That choice meant survival rates for Hellcat pilots exceeded those of any previous American fighter type. More pilots came home because the Hellcat brought them home, absorbing damage that would have killed them in lesser aircraft. The families who welcomed those pilots home owed debts to Grumman's engineers, to the factory workers who built each aircraft, and to the design philosophy that prioritized pilot survival alongside combat effectiveness. Speed won the tactical battles, but the Hellcat's comprehensive design excellence won the war. From the morning of September 1st, 1943, when Lieutenant Takeo Tanemizu first realized his Zero couldn't catch the American fighter pulling away above him, through the final combat missions of August 1945, the Hellcat rewrote the rules of Pacific air combat. Japanese pilots who had dictated terms for 2 years suddenly found themselves on the defensive, unable to leverage their remaining advantages against an opponent that controlled the speed envelope. The psychological impact of that reversal cascaded through Japanese naval aviation, contributing to the collapse of morale and effectiveness that characterized the final 18 months of the Pacific War. The F6F Hellcat didn't win the war alone. Strategic bombing, submarine warfare, amphibious operations, and countless other factors contributed to Allied victory. But in the specific domain of carrier air combat, the Hellcat was the decisive weapon. It swept Japanese naval aviation from Pacific skies with methodical efficiency, enabling every subsequent American operation. The speed advantage that Japanese pilots lost when they encountered the Hellcat was never recovered, and that loss ensured their ultimate defeat. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.